What if I told you that the fundamental laws of nature, things like the conservation of energy, aren't actually rules the universe has to follow? What if they're just side effects of something much deeper or much more beautiful? Today, we're diving into the incredible connection between symmetry and the very code of reality.
We all tend to think of physical laws as these ironclad rules, right? Things the universe absolutely must obey. But what if we've got it completely backward? What if these laws aren't commands at all, but just the inevitable fallout, the consequences of the universe's most basic, elegant property?
And that property? It's symmetry. So let's follow this golden thread, because we're about to see how symmetry doesn't just describe our universe, it literally dictates its laws, revealing this stunning hidden logic behind, well, everything. Okay, so here's the core idea, the pattern we're going to see over and over again. It's like a simple two-step dance. First, you find a symmetry in nature, some property that stays exactly the same even when you change something else. And second, that symmetry, through the sheer power of mathematics, guarantees that some physical quantity has to be conserved. It's that simple. Let's see it in action. We're going to start with the symmetries that you can actually see and feel, the ones that are running the show for everything from a spinning planet to the very fabric of spacetime itself. First up, rotational invariance. And it's a really simple idea. The universe doesn't have a built-in up or down or this way. It just doesn't care. If you build an experiment, say a clock, it's going to tick the exact same way whether it's facing north, south, or pointed straight at the ceiling. The underlying laws of physics are perfectly symmetrical when it comes to rotation. And listen, this isn't just a hunch. We know this for a fact. When physicists smash particles together in accelerators, the debris flies out uniformly in all directions. This is called isotropic scattering, and it's stone-cold proof that the laws governing those collisions don't play favorites with any direction in space. And here is the first big payoff. That simple symmetry of space, the fact that it looks the same in all directions, directly and inevitably leads to the law of conservation of angular momentum. It's the reason a spinning ice skater pulls her arms in to speed up. It's why Earth keeps spinning on its axis. The law isn't a rule, it's a consequence of the symmetry. So, we've talked about symmetry in space. Now let's level up to symmetry in space-time. This is called Lorentz invariance, and it's a cornerstone of Einstein's special relativity. All it says is that the laws of physics are exactly the same for you, whether you're standing perfectly still or cruising through space at 1,000,000 miles an hour, as long as your velocity is constant. Now, the consequences of this symmetry are pretty mind-bending, but they are absolutely real. It is the reason the speed of light is the same for every single observer, no matter how fast they're moving. And it's the reason that time literally slows down for super-fast particles in accelerators. These aren't just cool ideas, they're experimental facts that prove this deep, deep symmetry of space-time.
Okay, so we've seen symmetries we can kind of wrap our heads around in space and motion. But now we have to go deeper. We're heading into the quantum world, where the most powerful symmetries are completely invisible to us.
And this, for me, is where the story gets just unbelievable. It turns out that some of the most fundamental rules that govern our tangible world are actually consequences of symmetries that we can never, ever see. Okay, meet phase invariance. Every quantum particle has something called a wave function, and that wave function has a property we call phase. The best way to think about it is like the key of a song. You can play Twinkle Twinkle Little Star in the key of C, or you can play it in the key of D. It's the exact same melody, right? The relationship between the notes is identical, you've just shifted the starting point. Well, in quantum mechanics, you can shift the phase of a particle's wave function, and all the stuff you can actually measure, its position, its energy, they stay exactly the same. This isn't just some neat math trick. It's a core principle of how the quantum world works. The universe literally does not care what absolute key a particle is playing in. All that matters is how its phase relates to the phases of other particles. That's what creates the harmony of quantum interactions. And here is the punchline. This completely abstract, totally invisible symmetry of quantum phase is the direct, one-to-one mathematical reason that electric charge is always conserved. Think about that. Every single time you use anything electric, the law governing that flow of electrons stems from a symmetry that is fundamentally impossible to see. It's just incredible. So this amazing idea that these hidden symmetries actually create physical laws became this incredibly powerful tool for physicists, especially in the mid-20th century. It allowed them to find a secret order in what looked like absolute chaos. So, by the 1960s, our new particle accelerators were discovering a whole flood of new particles. I mean, we had protons and neutrons, sure, but then came pions and kaons and sigmas and lambdas. It was a total mess. They literally called it the particle zoo because there was no rhyme or reason to any of it. The first big clue to taming this zoo came when physicists noticed that the proton and neutron are almost identical twins, apart from their electric charge. So they proposed a new hidden symmetry they called isospin. Think of it like a coin. It's still a coin whether it's heads or tails. They realized that if you could just ignore the effects of electromagnetism, the proton and the neutron were just two different faces of the very same particle. This idea was a game changer, and it got expanded into an even more powerful symmetry called the Eightfold Way. This new idea, called SU3 symmetry, suggested that particles could be grouped together not just in pairs, but in these beautiful families of 8. Suddenly, it started to organize the entire particle zoo into these neat, elegant, geometric patterns. It was becoming a periodic table for particles. And you can just see the orders snapping into place right here with the baryon octet. Look at that. All of a sudden, these 8 different particles, including our old friends the proton and neutron, they weren't random discoveries anymore. No, they were all members of a single elegant family, their properties perfectly predicted by the rules of this hidden SU3 symmetry. So let's zoom out for a second and just look at the breathtaking pattern that's emerged from all this. This really is the secret code of our physical reality. And here it is, all laid out. You see the pattern, right? Rotational symmetry in space gives us conservation of angular momentum. That symmetry in spacetime, Lorentz invariance, gives us conservation of energy and momentum. The totally invisible phase symmetry, that gives us conservation of electric charge. And those abstract symmetries, like SU3, they gave us a deep understanding of the particle families. Every single time, a symmetry on one side, a conservation law on the other. This is the profound realization we've been building towards. The fundamental laws of physics are not just a random list of cosmic regulations that happen to be true. They are the shadows cast by the universe's underlying symmetries. The symmetry is the deep fundamental reality, and the law we observe is merely its consequence. It completely flips how we see the universe. And this, of course, leads us to a final, absolutely thrilling question. Physicists today are on the hunt for even deeper, more profound symmetries. You might have heard of supersymmetry, because they believe that hidden inside them are the undiscovered laws that could finally explain mysteries like dark matter and quantum gravity. The next great breakthrough in physics might not come from finding a new particle, but from discovering a new, more perfect symmetry.